Hey everyone, Dr. Tom McNamara back again for our course in trigonometry. In today's video, we are going to focus on a new aspect of the trig functions. So far, we have discussed right triangle trigonometry, which is very useful for indirect measurement. We've talked a little bit about identities, and we'll go into more depth in that on that topic later, which explores the algebraic relationships that the trig functions fit into. And in this series of videos, and this one and what comes next, we're going to talk about how trig functions can be used to model periodic phenomena. And a typical example that I've used in the past is something like this. If this is the, let's say this is the time axis, where this right here, that's midnight, and this is the temperature axis. We might expect a scenario like this. So at midnight, we expect the temperature to be kind of cool. We expect it to maybe even drop a little bit during the night, but then during the day, we expect it to go back up, peak in the middle of the day, come back down at night, and then, the next day we would expect a similar kind of cycle where the temperature rises, hits a max in the middle of the day, goes back down at night, and so on, and repeats like that. So as we'll see, these trigonometric functions, they oscillate. They are what we call periodic functions. So let's start out with something like this. I'm going to look at the value of cosine theta for various angles theta. So we're going to go in increments of pi over 4. So I'm taking steps of pi over 4 units until I get up to 2 pi. And this is, of course, in radians. Okay, so I got 0 radians, pi over 4, 2 pi over 4, which simplifies to pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which simplifies to 3 pi over 2, 7 pi over 4, and 8 pi over 4. Now, using our unit circle, using that unit circle model that we discussed before, we can read off the value of cosine for these various angles. Okay, so cosine of 0 is 1. Okay, we can see it on the unit circle right there. Root 2 over 2, 0. Now at 3 pi over 4, the cosine is negative. And then here at pi, cosine is negative 1. Still negative. At 3 pi over 2, cosine is 0. Root 2 over 2, and 1. Now, using our calculator, we could get an approximation for radical 2 over 2. It's approximately 0.7 if you want a decimal approximation there. So here's what I'm going to do. I'm going to plot the value of cosine theta for these various values of theta. All right, so we see the max value that cosine ever has is 1, and the min is negative 1. So on my y-axis, where I'm going to plot y equals cosine theta, the highest I need to go is 1, the lowest I need to go is negative 1. This is my theta axis right here. Okay, so okay. Now, These are going to be increments of pi over 2, pi, 3 pi over 2, and 2 pi. All right, so this is theta equals 0 right here. Theta equals 0, the cosine is 1. Okay, so I'm plotting the various values of cosine as the height, and the horizontal axis represents the angle that we're putting in. Okay, so at theta equals pi over 4, I'm approximately like 0.7, maybe right there. 0, negative 0.7, negative 1, 0.7, 0, 0.7, and then back to 1. Okay, so in this section, my cosine value is dropping, continues to drop, bottoms out here at negative 1, we're back up to 0, and then we're up like that. Okay, so that is part of the graph of y equals cosine theta. Now, the neat thing about the unit circle is not only does it let us know the value of cosine theta for angles between 0 and 2 pi, we can continue that. If we had, let's say, talked about an angle greater than 2 pi, well, you're just going to wrap around back again. Okay, so if we're talking about increments of pi over 4, well, this would be 9 pi over 4 over here, but that's just going around a full 2 pi plus an additional pi over 4 units. So we're going to get a repeat of what we had right here, and so on down the line. So if I were to continue this graph, to the right, I would get another copy of what I had right here. That would just get repeated over here. Okay, and just for the sake of completeness, this is 5 pi over 2, this is 3 pi, this is 7 pi over 2, and this is 4 pi. And if I were to extend it even further, I would keep getting copies of this picture over and over again. And that would even hold over in this section. Okay, this would be right here. Okay, so the graph y equals cosine theta is what we call periodic with period 2 pi. So in other words, cosine of theta plus 2 pi is equal to cosine theta. In other words, adding 2 pi to your angle, basically it doesn't matter. And if you think about the original interpretation we had of the trig functions as angles in standard position or the unit circle, it's easy to understand why. Okay, your angle tells you how far to rotate. If you add a rotation of 2 pi radians, that's equivalent to a full revolution. So you've come back around and you're in the same place. So adding 2 pi to your angle doesn't really change where you end up. So that makes sense right there, that identity. Okay, so this is what the graph of y equals cosine theta looks like. Okay, so I would recommend that you memorize this picture. In particular, where the cosine is 1, 0, and negative 1. Kind of, we're going to treat those as like our anchor points. Okay? Now, we do have 2 other graphs that I want to talk about. And we can do a very similar thing. We could go to our picture of the unit circle, and we could get the values of the sine function and the cosine and the tangent function and read those off. So in this section right here, let me give myself a little more space than that. On this graph, I'm going to plot y equals sine theta. Okay. So once again, we can see from our unit circle that the max value of the sine function for any angle is going to be 1. Sine of any angle is always going to be 1 at most. And the minimum that it can be is -1. Okay, so you can see from your unit circle diagram, that the sine function is 0 when theta equals 0. When theta equals pi over 2, the sine function is 1, back down to 0, to -1 here, back to 0. So the sine function would look like this. The sine function is also periodic, so if I wanted to know what does the graph look like over here, I would take an exact copy of the picture I've got right here and put it there. Okay? And the same thing would apply on the other side. You want to know what this section looks like? Take this exact thing and put it right there. So, we get this picture over here for our sine function. Okay, now, I want you to notice something about the graphs of sine theta and cosine theta. So sine theta is in the white. I'm going to redraw the picture of cosine theta, but I'm going to use blue. Is that coming up? Yeah, you can kind of see the difference. Okay, so cosine theta is over here. Okay, I want you to notice that the blue graph, the graph of y equals cosine theta, the left side is a mirror image of the right side. It's like an exact copy. Cosine theta has y-axis symmetry. That's called an even function. Okay, so just a couple things to note here. Cosine of negative theta, that is equal to cosine theta. This is a consequence of cosine being an even function. Okay, so if I talk about pi over 2 versus negative pi over 2, I get the same cosine. If I talk about pi versus negative pi, the value of cosine is the same. That's the mathematical language encapsulating what we just said right there. However, you look at the sine function, you'll see, okay, it's not quite a mirror image. This part is upside down. In other words, the y values have the opposite sign that they did over there. They're flipped. It's a reflection. So if you look at the left side, it's an upside down copy of the right side. So sine negative theta is equal to negative sine theta. So cosine is what we call an even function. Sine, that is what we call an odd function. And this is how it manifests itself mathematically. Graphically, it shows up with symmetry. Even functions have that left-right symmetry. The left-hand side is an exact copy of the right-hand side. With odd functions, it's an upside-down copy. Okay? Now, there's one more function I want to discuss here, and that is the tangent function. So this is going to be my theta axis, and then y equals tan theta. All right, now, one thing that is a little tricky about the tangent function of course, we know our ratio identity. We remember that. The tangent of an angle theta is equal to the sine over the cosine. Well, whenever you have this division, you got to be a little bit careful. You got to make sure you don't divide by 0. Cosine can be 0. And cosine is 0 when theta equals pi over 2. Okay, so the tangent function would in fact be undefined when theta equals pi over 2. So there's going to be a break in the graph of the tangent function. And the tangent function is going to look like this. As we approach theta equals pi over 2, the values of the tangent function are going to balloon up. They're going to get bigger and bigger and bigger as theta approaches pi over 2. And on this side, we'll have a copy that looks like this. Okay? And this is going to repeat over and over again. Okay? So, the tangent function is also periodic, but the period is pi rather than 2 pi. Sine and cosine function both have period pi. The tangent function has period 2 pi. So once again, we'd get this exact same picture over here, and that would repeat forever. Okay, so all your trig functions are going to be periodic. Most of them have period 2 pi. You got to be careful with tangent and cotangent. Those have period pi instead. Okay, so those are the basic graphs of the trig functions. So I recommend you draw out pictures for the sine function, the cosine function, and the tangent function. Memorize those pictures. And pay particular attention to what I call anchor points. When is the function 0? When is it 1? When does it have an asymptote? Those are especially important to remember from your pictures.